Have you ever heard of Galloping Gertie? No, it's not a racehorse. It was the nickname for a massive, state-of-the-art suspension bridge that danced itself to death in 1940. This is the story of the first Tacoma Narrows Bridge, a marvel of engineering that became a spectacular lesson in what happens when we misinterpret the warning signs nature gives us. In the late 1930s, Washington state was booming, and the need to connect Tacoma with the Kitsap Peninsula was greater than ever. The solution? A breathtakingly long and slender suspension bridge, the third longest in the world at the time. Designer Leon Moisseiff was a celebrated engineer known for his elegant and flexible designs. He believed a lighter, more graceful bridge was not only cheaper, but also more advanced. The Tacoma Narrows Bridge, with its thin steel girders, was the pinnacle of this philosophy. But from the moment it opened to traffic on July 1, 1940, something was. Even a gentle breeze would cause the bridge deck to undulate in long, rolling waves. It was unnerving. Drivers would watch the car ahead of them disappear into a trough, only to reappear moments later on the crest of a concrete wave. The locals quickly gave it the nickname Galloping Gertie. For some, it was a terrifying experience. For others, it became a quirky tourist attraction. People would drive from miles around just to experience the roller coaster ride. Now, you might be thinking, a bouncing bridge? It sounds like a major red flag, and you'd be right. But the engineers weren't completely oblivious. They knew about the motion. In fact, they had installed monitoring equipment to study it. The problem was, they were looking for the wrong thing. They were primarily concerned with the bridge's vertical movement, the up and down bounce. They installed electrical sensors, a kind of early warning system, to measure this vertical oscillation. They believed that as long as the bouncing stayed within certain limits, the bridge was safe. The lead engineer, Clark Eldridge, was worried. He pushed for additional measures to stiffen the structure, but the project was driven by a tight budget. Moisseiff, the primary designer, reassured everyone that the flexibility was intentional and that the structure was fundamentally sound. He argued the oscillations were harmless. The bridge's movements were observed, recorded, and studied, but the conclusion was always the same. It's just bouncing. The sensors confirmed this, showing the expected vertical waves. No one was seriously considering a different kind of movement, a more destructive one. This is where the story takes a turn. The engineers were focused on the gallop, but they missed the twist. For 4 months, Galloping Gertie did its thing, bounced and swayed, becoming a local legend. Then came the morning of November 7, 1940. The wind was blowing at a steady but not unusually strong 42 miles per hour. At first, the bridge behaved as it always did, with its characteristic vertical waves. The sensors were likely showing business as usual. But then something changed. The main span suddenly stopped its familiar up and down motion and began to twist. The bridge deck started rotating back and forth in a violent torsional flutter. One side of the roadway would rise while the other side fell, creating a terrifying seesaw motion. This was a type of movement the engineers hadn't anticipated, and one their monitoring system was really designed to warn against. Their focus on vertical bounce meant they were blind to the far more dangerous torsional stress building up in the structure. Imagine being on that bridge. The only person left was a reporter, Leonard Coatsworth. His car was stranded in the middle of the span. He tried to rescue his dog, Tubby, from the back seat, but the Cocker Spaniel was too terrified to move. As the bridge twisted more and more violently, the concrete cracked and huge chunks fell away into the water below. The steel cables groaned and snapped. Coatsworth had to crawl on his hands and knees to safety, thrown from side to side by the bucking roadway. From the shore, a crowd watched in disbelief. A local professor, Farquharson, who had been studying the bridge's motion, was there with his camera, capturing the unbelievable event. The twisting became more and more extreme. The deck was tilting at angles of up to 45 degrees. The strain on the steel was immense. Finally, with a deafening roar, a 600-foot section of the main span tore loose and plunged into the Puget Sound below. One by one, the other sections followed, leaving the two great towers standing alone, with the side spans sagging limply. Galloping Gertie was gone. So what went wrong? Electrical sensors didn't technically fail. They did their job of measuring vertical movement. The real failure was a failure of imagination and interpretation. The engineers were monitoring the symptoms they expected, not the ones that would prove fatal. They saw the bounce, logged the data, and concluded it was manageable. They were so focused on the gallop that they missed the deadly twist that was building up. The culprit was a phenomenon called aeroelastic flutter. The steady wind flowing over the bridge's thin, solid girders created vortices or swirling eddies of air. At a certain wind speed, the frequency of these vortices matched the bridge's natural torsional frequency. It's like pushing a child on a swing. If you push at just the right moment in each swing, the swing goes higher and higher. The wind was pushing the bridge in its twist, and each push added more energy, causing the twisting to amplify until the structure tore itself apart. The bridge wasn't strong enough or aerodynamically stable enough to dampen these forces. The solid girders acted like a wing, catching the wind in a way that encouraged the twisting motion. The original design, based on established theories, simply didn't account for this complex interaction between wind and a light, flexible structure. The collapse of the Tacoma Narrows Bridge became one of the most famous engineering failures in history. Not because of a lack of data, but because of a misunderstanding of what that data meant. The warning signs were there from day one. The constant bouncing was the bridge screaming that it had a problem with the wind. The monitoring system was in place, but it was like a doctor checking your blood pressure when the real problem is in your heart. They were looking at the wrong vital sign. This event revolutionized bridge design. Engineers learned that it's not enough for a bridge to be strong enough to hold up its own weight and the traffic on it. It also has to be aerodynamically stable. After the collapse, new bridge designs began incorporating open trusses or streamlined, wing-shaped decks that allow wind to pass through or around them smoothly, preventing the buildup of destructive oscillations. Wind tunnel testing became a mandatory step for any major suspension bridge project. The story of Galloping Gertie is a powerful reminder. It teaches us that data and monitoring are only as good as our ability to ask the right questions. We can have the most advanced sensors in the world, but if we're looking for the wrong signals or ignoring the obvious, we're flying blind. It's a lesson about humility in the face of nature and the critical importance of understanding the fundamental forces at play, not just the ones we expect to see. The next time you drive over a long suspension bridge, take a moment to appreciate the invisible engineering that keeps it stable. That stability is, in part, the legacy of a dancing bridge in Washington state that gave its life to teach us a lesson we would never forget. Thank you so much for watching. If you found this story as fascinating as I do, be sure to hit that like button and subscribe for more deep dives into the triumphs and failures of engineering. See you in the next one.